Okay. Let's review a little bit. This is from the 3-variable K-map. And now look at this. So these two right here. Now this this up here is given the function. But where that comes from is you're looking at these particular items here: 2, 3, 4, and 5. The 2 stands for m sub 2. So that's why there's a 1 there. The 3, there's a 1 there. The 4, there's a 1 there. And the 5, there's a 1 there. So by default, what's in the other places? 0. And so we're going to see how this is connected to the next section and how they kind of swap. Now, if I group these two together, well, they both have a x of 0. And remember, 0 means a complement. So that's an x complement. Now, if I look at this column and this column, M3 and M2, they both have the same first item, which is our y. The yz over here tells the order. So the y's are the same. They're both 1s, so that's why it's just y versus y prime. Now, since the z's are different, here z is 1, and here z is 0. Since the z's are different, that's why that drops away. Down here, same idea. This one right here, well, no matter what, the x is always 1, which is, okay, I'm getting that backwards. Okay, x being 1 means it's just the normal x. Coming up here, I got 0, 0, and 0, 1. This is for the columns of M4 and M5. I see they're both started with 0, so that's the same. So the y is the same. And that's where the y prime comes from. And then the z is different. Z is 0, z is 1. And since the z is different, that's why it drops away. And then you would add those together. Now that gives us our, it says simplify the Boolean function. That gives us our simplification of that Boolean function. Okay, so let's go over to the product to sum simplification. Bizarre. See this down here at the bottom? Yeah. It's got like some blender thing down here. Don't know why it's doing that. Okay. Now the product sum simplification. The minimized Boolean functions derived from the map in all previous examples were expressed in the sum of products form. What we just reviewed with that one example. With a minor modification, the product to sums form can be obtained. The procedure for obtaining a minimized function in product to sums forms follows from the basic properties of Boolean functions. The ones placed in the squares of the map represent the min-terms of the function. The min-terms not included in the standard sum of products denote the complement of the function. Hi. There you go. Hello. We're just we were just reviewing a little bit from last time, or maybe 2 times ago. Then talking about the product to sum simplification. And this talks about the procedure for the product of sums. Procedure for obtaining a minimized function and product sums follows from the basic properties of Boolean functions. The ones placed in the squares of the map represent the min terms. The min terms not included in the standard sum of products form of a function denote the complement of the function. Now, the complement of the function is maybe not quite what you think, but we're going to see that. From this observation, we see that the complement of a function is represented in a map by the squares not marked by ones. So, talking about the zeros. If we mark the empty squares by zeros and combine them into valid adjacent squares, we obtain a simplified sum of products expression on the complement of the function, i.e. of f prime, the complement of f. Complement of f, f prime gives us back the function f. So they undo each other in a product of sums form. Consequence of De Morgan's theorem. Because of the generalized De Morgan's theorem, the function so obtained is automatically in a product of sums form. We will show this by an example. Now, just in general on this, when we look at this, it says simplifying the following Boolean function in the sum of products form and product of sums form. Remember the 0, 1, 2, 5, 8, 9, 10 refer to the individual squares. So 0 is m sub 0, which we put a 1. m1 is 1. m5 is 1. m8 is 1. m9 is 1. m10 is 1. And all the rest are zeros. Now, if I were to go through and focus on the procedure we did last time, and I came up with, make sure that's the same one. Yeah, it is. Come up with this right here, BD plus BC plus ACD. Then that would give us this breakdown here. It's actually a little bit easier than that, though. If you got AB plus CD plus BD prime, that's our F prime. Now, that's the sum of products, isn't it? We've got this times this, this times this, times this, and we're adding them together. To change that into the product of sums, you got AB here, don't you? And what's between them? And? Then, you notice down here, they got A prime and B prime, and there's a plus or an or between them. So A went to A prime, B went to B prime, and then you change the operation in between them. Notice here, we got CD, and it became C prime plus D prime. This one is BD prime, and it became B prime plus D. So if you have this right here, you can just kind of reverse it, can't you? That's why I said that the complement maybe is a little bit different than what you might think. It's easy to see that the complement of A is A prime, right? That's simple. But the complement of the and is an or. See, that's something we really haven't explored, but that's demonstrated here. Does that make sense how to switch those? Now, what I find interesting, though, is up here, see how we get BD plus BC plus ACD? And if you look at the product of sums over here, does that look like it follows the same pattern? Doesn't, does it? On some of these, you'll find that there's a unique answer. In some of them, there's multiple answers. And that can be frustrating. When you get an answer that doesn't match back to the book, and you're sitting there wondering what you did wrong, and potentially you didn't do anything wrong. So, part of it is how you pair things up. And we talked about the prime implicants, and I'm going to show you a video on that, where if you use the prime implicants, then you should come up with the same answer each time. But if you don't, you can go other ways. You can come up with variations. Let's see. The gate level implementation of simplified expressions obtained in this example is shown in this figure. Some of the products expressions implemented in A with a group of AND gates. Okay, so they're showing the one for up here. And so you see the pattern we have here. We got our B prime, D prime coming in, and they don't bother to invert those like we saw before. They just have them to come straight in. And then there's the and between them. And then down here, this is B coming, or B prime coming in down here with the C prime and the and in between them. And here's a C prime coming in down here where we got A prime, C prime, and D. A prime, C prime, and D. And then this over here is our OR, and that's how it comes a plus between all of them. Now the breakdown over here, using the product of sums, you see we got our A prime here, and you got our B prime, and then there's the OR symbol, and there's a plus in between them down here. Down here, again, a plus between them. Down here, a plus between them. And then over at the final end, the final here is the and symbol, which means we're taking this and this and this, which looks like multiplication. Configuration. Outputs of the OR gates connected to the inputs. Okay. In each case, assume the input variables are directly variable in their complement, so that's why they don't invert them. Inverters are not needed. Configuration pattern established is the general form by which any Boolean function is implemented when expressed in one of the standard forms. And gates are connected to a single OR gate when in the sum of products. OR gates are connected to a single AND gate when in the product of sum forms. So we're talking about this in symbol. Either configuration forms two levels of gates. Thus, the implementation of a function in standard form is said to be a two-level implementation. Two-level implementation may not be practical, depending on the number of inputs to the gates. Is there any questions on that diagram? Now for, I haven't priced these or anything like that, so I don't know from a design standpoint if one's cheaper than the other or what, but that's how you can do it both ways. Okay, this shows the procedure for obtaining the product sum simplification when functions are originally expressed in sum of min terms, a canonical form. Procedure is also valid when functions originally expressed in a product of max terms, canonical form. Consider, for example, truth table defines the function f in this table. In sum of min terms, the function is expressed as this way, 1, 3, 4, 6. I'm not going to go through that, but if and it's kind of strange how they do it anyway. I wish they didn't do that. But what's example 3.7? When you compare it to this right here, do you got x, y, and z? The one up above you don't, but maybe you do on the previous page. Is that on the previous page have x, y, and z? No. I helped one student. They want some extra help on some of the problems, which is fantastic. If you ever need any, holler at me. But we worked some of the Boolean algebra, and there's one of them where it created I didn't even think about it. It had B, C, and D in the homework. And I automatically added an A in there. There was no A to be anywhere found in the problem, or that part of the problem. And I automatically put it in there. And I gave the answer in the back of the book. He asked after I was done, he said, "Why did you put an A there?" And I didn't even think. I just saw B, C, D. I thought it should be an A. Problem didn't indicate it. So kind of the way they go back and forth between the letters and so forth, I'm not really crazy about. But anyway, what they're demonstrating here is when you got the sum of products, you got 1, 3, 4, and 6. If you look at 1, which is right here, it's a 1, isn't it? Remember, this starts at 0. That's 0, 1, 2, 3. So for 3, there's a 1. For 4, there's a 1. Here's 5, and here's 6. 6 is a 1. So for the sum of products, our function is equal to 1 at those places there. Now, on the other hand, if you look at the product of sums, 0, 2, 5, and 7, at the 0th position is 0. At the second position is a 0. At the 5th position, 0, 1, 2, 3, 4, 5, it's a 0. At the 7th position, 0. So they're showing a relationship between the two, the complement of it. In other words, the ones of the function represent the min terms, 0 represents max terms. The map for this function is shown in the figure. One can start simplifying the function by first marking the 1s for each min term. That the function is a 1. The remaining squares are marked by 0s. If instead the product max term is initially given, one can start marking 0s in those squares listed in the function. The remaining squares are then marked by 1s. Once the 1s and 0s marked, the function can be obtained can be simplified in either one of the standard forms. For the sum products, we obtain the 1s to obtain this right here. So we got x prime z. Let me think that through. This first row, we're looking at M1 and M3. This first row, x is 0. X is 0 is a x prime, isn't it? Now, if I look at the columns for M1 and M3, they both have the same z. They're both z is equal to 1. And z equals 1 is just z. Now the y changes. Here's y in the column for M1, y is 0. For the column for M3, y is 1. So the difference, so that's why that one cancels away. Plus, and then if I focus on these down here, they're all in the same row where x is equal to 1. And x equals 1 is just our normal x. And then there's, let me see, y is 0 in the column for M4, and y is 1 for the column for M6. So they're different, so that's why the y drops away. And then for this column, it's z is 0. For this column, z is 0, which is why the z prime is there. Okay, so we have that. Then for the product of sums, we combine the zeros to obtain the simplified complemented function. So we got xz. Now, let me draw this. You probably can't see my mouse even moving on the screen. Okay, so we got Okay, so um, if we look at this zero, we'll look at these zeros here first. So we're looking at these two down here. Now up here, when we did these two here, we said x equals 0 represented what? X prime? Now down here, if we look at these ones I've circled, so we're looking at these right here. Then down here, we got x is equal to 1. And notice that they have that x right there. That's where we came up with this here. And then if you look up here, we got our y is equal to 0, y is equal to 1, so that drops away. You got z is equal to 1, z is equal to 1. Wait a minute, I'm looking at the wrong thing. Okay, these are comparing these two. So we had the same x value, both x equals 1, and we got x, didn't we? Now, if we look at this right here, what is x? X equals 1. And look what we came up with down here. We came up with x, didn't we? Up here, the z's are both equal to the z's. 1. So for these middle two zeros, the ones I've circled here, then they're both z is equal to 1. And notice that they have xz here, don't they? Everybody see where that xz comes from? Okay. So this x prime z prime. So if I'm looking at this one here, and I'm looking at this one here. So those are the two boxes we're looking at. Well, both of them are what? X equals 0? Because they're both in the same row, aren't they? And notice they put the x prime down here. Now the z, well, the y's are different. This is y's, this first column here, the m0, y is equal to 0. This last one, m2, the y is equal to 1. Since the y's are different, it drops off. But notice that the z are both what? 0? So they're both 0. And notice down here, they came up with z prime. Now, when you look at this one and this one, would you necessarily that they look like complements to you, the f and f prime? Not necessarily, right? I mean, they are complements based upon the table there. But then you come down here, after you look at just the zeros and come up with that mapping. Notice the xz, we're taking the complement of it. The x becomes x prime, the z becomes z prime, and instead of there being an and between them, there's an or, a plus. The x prime here becomes x, the z prime becomes z, and instead of there being an and between them, a multiplication, what looks like a multiplication, there's an or, a plus. Is that clear as mud? Let me go grab I should have brought my drink. I'll be right back. Okay, let's look at some examples. This is the end of chapter 3. And page something. In the book, this is on page 140. And I got how they, where there's a choice, I got down where they have these written. Okay, so we got 0, 2, 4, and 5. We're looking at 3.1, part A. And I guess I ought to write down the problem. F of XYZ is equal to 0 to 4 and 5. The instructions say to simplify the following Boolean functions using 3 variable K-maps. So let me draw a picture. X, our Y, and our Z here. And let's see, this is 0, 1. 0, 0, 0, 1, 1, 1, 1, 0. And M naught is the first square. So we'll put a 1 there. M2 is our last square. We'll put a 1 there. M4, so small I can't see it. I think it's this one here. And M5 is this one here. So by default, there's zeros there. Now, we want to pair up the ones, and so they use a logical connection. Putting these two together. And then they use the logical connection of these right here. So If I look at the red, assuming you're not red-green colorblind, for our x is 0, isn't it? How about the y's? Like, what would the y be here? 0? How about the y here? 0? Or no, 1. Because remember, your y is the first number. Yeah. 0 and 1. So they're different, right? So the y's drop away. Now the z's in both of these are both what? 0. So x is 0 and y is 0. So what's this going to give us? X prime, z prime. Now if I look at the green, x is over here on the left-hand side. X in both cases is equal to 1, right? So what am I going to put? X? Because remember, the 0 here represents x prime, and the 1 represents x. So if I'm looking at the green here, which one's different, y or z? Z. Yeah, because z is 0 here and z is 1 here. So z drops away. Now, in both these cases, y is equal to 0, isn't it? So what would that be? Y prime? So that'd be y prime. Now, instead, if I focus on the, and this isn't what the problem's asking for, but instead of focusing on the ones, I focus on the zeros, so the complement. So I'd have a pair here, and I'd have a pair here. There's a reason why I wouldn't have to consider this pair, which that video should demonstrate here in a little bit. But if I can focus on this, let me write down my values again. We got our x, y, z. This is 0, 0, 0, 1, 1, 1, 1, 0. And this is 0 and 1, remembering what these represent and so forth. So for this top, I should have done two different colors. This top red. What would x be? X prime? Because they're both the same, aren't they? They're both x equals 0. Now looking at this top two red ones, which one's different, the y or z? The y, because y is 0 here and y is 1 here. So z's are the same. Z is actually both equal to 1. So what would I put down here? Z. Now if I focus on the bottom two red ones now. X in both cases is equal to 1, isn't it? So what do I put here for x? X. What's different, the y or z? Z. Because in this column, z is equal to 1. In this column, z is equal to 0. So z's drop away. The y is the same. Y is both equal to 1. So what would I put down here? Z was different. Y. Okay. So then our goal is to rewrite this from the sum of products to the product of sums. So what would this first parentheses say?
X prime. Would it be X prime?
No.
No.
Because it flips. It goes from x prime to x, and then z goes to z prime. And then this one would go to x prime plus y prime.
So would that be the answer for A?
No.
Or for the last one would be the answer?
The answer for A is actually
that one.
This one right here. I'm just showing a relationship between the two.
Yeah.
So if you understand how to get the this first part, the finding this product of sums is basically just look at the zeros, and then you flip it like what you see there.
So do you have to do what you did on that one, the first one?
No, the only thing you have to actually on homework will be just that. Now I'm just showing the connection between the two. And that's what they're, if I flip over, see, this is where you got this set up down here. And if you focus on just the ones, then you get, oops, up here. Focus on just ones, you get this right up here. So just that, and that's like what we're doing, the instructions are actually asking for. If instead you don't focus on the ones, but you focus on the zeros, then you get this one down here, which is f prime. And then to get f, you then go backwards, rewriting the outer addition as a product, and then the multiplication as a addition. Take a look at another one of those. Maybe. Oh, there it goes. Save. Okay, so let's look at B. We got sum of 0 to 4, 5, 6. If I draw my picture, 0, 1. 0, 0, 0, 1, 1, 1, 1, 0. 1, 1, 1, 1, 1. I'll put zeros here by default. And pairings they use. Actually, these aren't even labeled. I better make sure I did the right one. 0s, 1, 2. Where's 2? 2. 2's over there. 4. There's 4. Okay, 4, 5, 6. Okay, that's the right one. The pairings they did is they paired these two together. They paired these two together. So I can see my mouse. There. Paired those two together. And then they paired these two together. Okay. Remembering, what does the 0 represent for x? Prime. So I can see my mouse. There it is. So that's x prime, and that's x. So up here, the 0 would represent y prime or z prime, this case may be, and the 1s again represent y and z. Okay, so we'll look at the red over here first. What would the red be?
Which one's the bottom one or the right one?
Or this red here on far right. Actually, let me label these. This will be y prime, z prime. This one would be y prime, z. This one would be yz. And these two would be y, z prime. Okay, so I'm looking at this far right, these two for the far right column. This red here, I need to use a different color, I guess. What would that give us?
X prime, y, z prime.
YZ prime. Because what's different there? The x's. So x's drop away. And you can actually look above. This was actually one of the videos I saw. The person actually wrote up above like this. And I thought that's pretty cool, actually, because you can then visually see the YZ prime real close. In this last column here, y is always equal to 1, z prime is always equal to 0. Okay, now if I look at the orange. The orange is the bottom two right here. Well, first off, what can I say about x? It's not prime, and they're both the same, aren't they? Which means there's going to be an x here. Now, if I go up to the top here, you see I got y prime, z prime, y prime, z. So what goes here? Y prime. Because the Y primes are the same, aren't they? This one has a Z prime, this one has a Z. Since that's different, that's why it crosses off. And now for our green. The green is this far left column, if you have trouble seeing that color there. What can I say about X on both of those? They're different, isn't it? So the X is going to drop away. In this column, if I go straight up here, they're both Y prime, Z prime. Y is equal to 0, Z is equal to 0. So this would be Y prime, Z prime. Oftentimes when you share an item like this, where they share an entry, you're going to find that you have like an odd number, so you can combine things together. What do you notice that I can combine together here? These are both YZ prime, aren't they? What happens when they're the same?
1.
I think isn't it like X plus X is equal to X? It's on 47. I think you're thinking when you multiply them. But I could be wrong. My memory's not that great. Is it? Okay. So YZ prime plus YZ prime gives us YZ prime. Plus X, Y prime. I dropped something, didn't I? Hold on. I screwed up. Because what should the green have been? Not YZ prime. It should have been Y prime Z prime. Boy, my eyes are getting bad. Because if you look up here in this green column, up there I wrote down Y prime Z prime. Okay, that changes it.
Shouldn't you be doing F prime?
Yeah, we'll be doing F prime here shortly. Now, if I look at YZ prime and Y prime Z prime, what can I factor out of that?
The Y prime. Wait, the Z prime.
Z prime. And that leaves us Y plus Y prime plus X Y prime. And Y plus Y prime, I think, gives us 0. Or no, 1. Why can't I remember things like that?
I think it's 1.
Is it 1? I'm pretty sure it is.
I think.
Okay, so then that gives us Z prime times 1, which is Z prime plus X Y prime. Okay, so now if we focus on the other way, we got our X, we got our YZ, 0, 1. That's X prime, this is X. This is 0, 0, which is Y prime, Z prime. This one is 0, 1, which is Y prime, Z. I'll make them a little bit bigger so hopefully I don't screw up. YZ. And this will be YZ prime. Now where my focus is going to be is I'm focusing on the zeros. And like you said, this is a complement that we're looking at here. So I'm going to pair these two together. And that'll be like group 1. In blue, I'll pair these two together. That'll be like our group 2. So for our F prime, okay, so I'm going to focus on the red. Looking at these two red ones, what can I say about X? X is the same. So specifically, it's what? X prime. Looking again at the red, which is different, the Y's or Z's? Y. This one's Y prime. This is Y. So the Z's are the same. So this will be X prime Z. Now, if I focus on the blue, the G group 2, G2, what can you see about the X's? Different. So the X's drop away. They're both in the same column. So if I go straight up, the Y and Z are both the same. They're both equal to 1. So this would be YZ. Again, write that as a product of sums. I'm going to have parentheses here. What am I going to put inside of parentheses? X plus Z prime. Remember how the X prime here flips to the complement, X. The Z flips to the complement, Z prime. And then you change your multiplication, your and, to a plus or. And over here, what does Y become? Y prime. How about the Z? Questions on that? I got some video, a couple of videos to show, and then an example I thought was pretty good demonstrating that. So let's take a look at those. Hopefully you'll be able to hear this. Hmm. I'm not sure if that's been playing. Let me do it back. Huh. Got through quite a few. That must be it. Let me pause that. Figure out how to turn the volume on. Can you hear that? Now you're going to find that both of these kind of take different approaches to doing that same idea as what we just looked at, which I thought was interesting. Do you see why those are prime implicants? Everything else is used. Yeah, everything else is used twice, isn't it? You start looking at the like this 0 here is used by this rectangle, and it's also used by this rectangle. This 0 right here is used by this rectangle and used by this rectangle. This rectangle here, this is used twice, but this one's only used once, isn't it? And same down here. Now, where the focus is put on then is the pairings that included prime implicants, and that's what he'll talk about here shortly. Okay, so C and D are both the same here, aren't they? So see, he jumps directly to this, where you just write the F down. And since C is equal to 0, then you put a C down. And D is equal to 1, so you put D prime down, or the complement of D. Over here we said X prime is 0, didn't we? This was C is equal to 0 here, isn't it? But what did we put? C. So it flips around. So if you're going to write directly your sum, not do that step I showed you, but if you're going to write it directly, then you have to keep that in mind. That's the reason why when I started working this, I was writing this down. And because it messes you, it flips over to the opposite when you look at the other side. Okay, so this is our C, which is 0, which we just have C. D is 1, so that's where we get the D prime, or they got D bar, but that's complement of D. Coming straight up from the two pairings here, what's different is A, so that's why A drops away. And they both have B is equal to 1. Again, the 1 here indicates that it's complement. Does that make sense on where they come up with that? This might be a little bit easier to use this method, definitely on where you have 4 variables. So again, we're focusing on these two down here now. Okay, so going straight up, these two are in both the same column, so the A and B are both the same. A is 1, so that's where we get the A prime. B is 0, so that's where we get the B. Now coming over to the side here, as you pointed out, the C's are both 1, and that's where you get the C prime at. Okay, so doing this one down here and this one on this side. So wrapping around. I like use of the colors here where you can really show it good. I have trouble showing that. For this one, if I go straight up here, A is 0. If I come straight up here, A is 1. So that's why the A drops away, because it's different. If I come straight up to here, B is 0. I come straight up to here, B is 0. So that's where they get just the B. Coming over the side here, C is always 1, D is 0 for this row. So C is 1, that's where we get C prime, and D is 0 is where we get our D. Back it up just a little bit. This is a pair he's talking about, because those didn't include any prime implement, did it? So again, we're looking at these two right here. And if I come over, we'll go to the top, I guess A first. A is 1 here, A is 1 here. It's the same, so that's why I have A prime. B, if I come up straight up here, B is 0, B is 1. Here, B is 0, it's different, so that's why B drops away. If I come over to the side here, C is 0 and D is 0 for everything in this row. So that's where we get our C and our D. Now, if you use the prime implicants, then that'll give you the optimal one to use. You know, there's lots of different ways you could configure some of these, but if you use the prime implicants, then that works out well like that. Questions on that one? Let me close that. This next one's interesting. Let me see, which one did I click on? I don't understand everything he says, but I really like how he writes on here, and it's just so easy to see. I apologize for this network connection. He talks about over here, he doesn't really say it, but this is product of sum reduction using K-map. In your square over here, Each square of the K-map represents a max term. Remember, that's the uppercase M, isn't it? And I don't remember the numbering, but he'll go through and he'll put the. Did you have questions? No. Okay. It says that the map's filled by placing zeros. Rules for deriving it. Rules for deriving it exactly the same as that SOP. What's that stand for? Sum of products of sum. Not piece of. So keep it clean. Except that adjacent zeros are encircled in graphs. Again, that's what I'm emphasizing to you. Instead of focusing on the ones, we focus on the zeros. One major difference is that in the POS K-map, complemented letters represent ones, whereas uncomplemented letters represent zeros, which is just the opposite. So. I'm going to skip ahead a little bit. This is what I especially liked that he did. Remember on that one problem where I put the primes above with multiplication between them? Notice here I got C plus D, C plus D prime, C prime plus D prime, C prime plus D. The 0, 0, again, the zeros represent just normal letters. The 1 represents the prime. Putting these across the top and on the side, you'll find helps in working a problem, I think, if you can't visualize it that well. That's why I'm showing both of these examples. They're both kind of the same idea, but he does a little bit different. Now, I think he skips over, and I think he's doing it bilingual. Because some of the words are just like, I don't understand what he's referring to. He's going through and numbering them all. And notice he's putting zeros in. For the 0, 1, 3, 5, and so forth. Remember, when you're grouping these together, if you have 4 adjacent like that, you can group those as 1. And so that's what he's doing. He's grouping that. He calls that as group 1. The previous examples I showed you, they had to be in pairs, didn't they? And he's just generally talking about the max terms. This is M1 plus M3 plus M5 plus M7. Here's group 2. Now you can share one if you need be, if you got an odd number. So that's why he includes in this 7 again. And group 3, to include this 0 here, he needs another 0 because they got to be even. Excuse me. So that's why you got M0 plus M1. Then he's talking about group 1. I would let you listen to him, but I see our network people wander around the hallways, so I think there's something wrong with the network, especially since it won't play a YouTube video. Okay, group 1. Looking at these right here, we got A plus D prime. You see why it's A plus D prime? Because look over here, what are the same? The A's, right? So the A's are the same for these. If you look up here across the top, what's the same? The D primes? And that's why you have A plus D prime. So again, by putting that up here with the letters, I think it's visually, you can just see it so much easier. And then he goes to group 2. And that's B prime plus C prime. If I go to group 2, this square here, if you come over to the far left, the A's are different, so they drop away, but they both have B prime. So that's why you have the B prime plus. And then you go across the top, see how you have a C prime, both of those? They're the same, but the D's are different. This is D prime, this is D. That's why the D drops away and you're left with C prime. And then our last pairing right here, A plus B plus C. Well, oh, no, I see this one up here. I was wondering, that's not A plus B plus C. This is group 3 up here. The A plus B, since they're on the same row, is automatic, right? So A plus B carries down. Now the C, if you look up here, they both start with just C, don't they? So that's why that carries down. And notice the D and D prime are different, so that drops away. Okay, so group 4 is this one right down here. Okay, so C prime. If I come up here, C, well, they're all in the same column, so automatically C prime plus D is there. If I come over to the side here, I see they're both A prime, and that's why they have an A prime. And if you put those together as a product, then that's where it gives you the product. Questions on that one? Like I say, I'll put those links out there for those, but. And this was what I want to demonstrate here. See how it says since there are no essential prime implicants in our example, then we need to choose from all prime implicants of minimal cover. And there are two possible answers. So the reason why I show this is so if you're comparing your answer against the back of the book, don't get frustrated. If you get the wrong answer, it could be you're doing it right. It just depends on how you pair things up and so forth. You see here, the pairing they have here, they'll pair these two together, pair these two together, pair these two together, these two, and they go through all that. Versus over here, the pairings they chose here. Now I cheated. I printed off the solutions for the problems at the back because I wanted to do the pairing the exact same way as the book did. So, if you check your answer, you'd say, oh, you got a different answer again. Yeah, sometimes you do. Does that make sense how you can have different answers depending upon the pairings? Now, if you got prime implicants, then that's different. Again, I'll put the link out for that one also. That, close that. Let's take a look at one more example. Since I did such a wonderful job with the 4 variables last time, I'm not going to go down that road again. That's why I chose 2 videos to show you with the 4 variables, 4 literals. Let me choose another 3. In case you're wondering what I'll ask for you on a test, I won't ask for 4 variable K-maps. This will just be a homework. It'll be mainly the 3 variable that I'll focus on. Okay, so let's take a look at 3.1 part C. And that says that we got f of x, y, z is equal to 0, 1, 2, 3, 5. So this is our x, this is our y and z. And this is 0 and 1. In terms of this, what's a 0? Prime? I'm writing this down because remember how it flips depending upon the method you use to find the product of the sums? So I want to make sure I don't screw that up. Okay, so then 0, 0. So let's see, 0 is prime, so this would be y prime, z prime. This is 0, 1, which would be y prime, z. 1, 1, which would be yz. and 1, 0, which would be y z prime. Okay, and they say put it in 0. Yeah, just look at it. 0, 0, 0, that'd be that one. This is 0, 0, 1, which is 1, so that'd be that one. This one is 0, 1, 1, that'd be 3, that's on there. This one would be 2, so that's on there. 5. This is 1, 0, 0. That's 1, 2, 4. That'd be 4. That's 0. 1, 0, 1. That'd be 1. This is 4. 4 plus 1 is 5. And this would be 1, 1, 1, which is 4 plus 2, 6 plus 1 is 7. So that's 7. That's a 0. Remember how this goes? You can concatenate this together. This one's a 1. And then a 1, 0 here. And this is 1, 2, 4. So 4 plus 2 is 6. So this one's be 6. So that'd be 0. So make sure I match that up. Yeah. Okay. So we're going to pair together the 1s. And here's 2 we can pair together, right? Although I could do them individually and show it. What does this entire row give you? The what? Well, y would differ. Sometimes it's y is prime, and sometimes it's y. And sometimes it's z, and sometimes it's z prime. Well, let's do it. Let's break it apart. Okay, so if I did this pair here, and I did this pair here.
You gotta guess here, is it x prime?
Exactly. Yeah, since the y's and z's all differ like that, then that entire row is going to simplify and automatically give you x prime. So when you see things like that, you don't have to actually go through all the work. You can just write down x prime. Okay, this first one here, let's see. Or first two, I should say. Let me see, they're both x prime, so that's going to be there. Y prime is the same, but the z's are different. So this would be y prime. These next two here, the x prime is still the same. The y's are the same, so that's going to carry down. And z prime are different, so it just drops away. And then our red, this right here, the x is different because they're both in different rows, but they're both in the same column, so it's going to be y prime z. Now, if you notice these first two here, they both have an x prime. So if I factor that out, that gives us y prime plus y prime z. And y prime plus y gives us 1, I think. So x prime times 1 is x prime plus y prime z. Okay. So then, if I focus on the zeros. If you wanted to, you wouldn't even have to write down the ones because they're really not even bearing at this point. We would have to pair these two together, wouldn't we? And since this one's an odd number, I had to share this one and pair it with this one over here. So if I look at the red first, the x is 1 on both of those. So it's the same, isn't it? That'd be x. If I look straight up in my red, xy, exactly. Plus, and how about the blue? What would it be?
X z prime.
Let's see. Okay, y prime, y. Those are different, so those drop away. Z prime. Does that make sense? Because we're looking at this column and... Oh, wait a minute. Eyes are getting off. So yeah, we're looking at this here and this here. And they both share a Z prime, don't they? The what? I look at these too long. They just start, my eyes just start. So then, again, I like this technique because x prime is always 0, x is 1, and y and z and so forth. Helps me keep it straight. What's this become? X prime plus y prime. And then times z. Questions on that? Clear as mud? Well, that's the end of that section. Let's start talking about the next section. The don't care conditions. Okay, a logical sum of the min terms associated with the Boolean function specify conditions under which function is equal to 1. The what? The function is equal to 0 for the rest of the min terms. This pair of conditions assumes that all the combinations of the values for the variables of the function are valid. In practice, in some applications, the function is not specified for certain combinations of the variables. As an example, the 4-bit binary code for the decimal digits has 6 combinations that are not used and consequently are considered to be unspecified. Functions that have unspecified outputs for some input combinations are called incompletely specified functions. In most applications, we simply don't care what value is assumed by the function for the unspecified min terms. For this reason, it's customary to call the unspecified min terms of function don't care conditions. These don't care conditions can be used on a map to provide further simplification of the Boolean expression. Now, how they look. You see these x's here? So instead of having just zeros and ones, we have some x's in there. And that's what they're referring to. The Quine-McCluskey method uses a tabular format as an alternative to the K-map method used in our examples. As such, it is suitable for implementation in software. A don't care min term is a combination of variables whose logical value is not specified. Such a min term cannot be marked with a 1 in map because it would require a function to always be a 1 for such a combination. Likewise, putting a 0 on there is not valid. To distinguish the don't care conditions from 1s and 0s, an x is used. So they put an x there. Thus, an x inside a square of the map indicates we don't care whether the value is 1 or 0 or 1 because it really doesn't matter for what we're designing. Is assigned to the f for the particular min term. In choosing adjacent squares to simplify the function in the map, the don't care minterms may be assumed to be either 0 or 1. When simplifying the function, we can choose to include such don't care minterm with either the 1s or 0s, depending on combination gives the simplest expression. Okay, so they say we got to simplify the Boolean function. We got 1, 3, 7, 11, 15, which has these don't care conditions. Now, looking at this, the 1, 3, 7, 11, 15, that does not mean that these will always be your don't care conditions. They'll be different based upon different scenarios. All they're telling us here is these are the ones we don't care about. The minterms of f or the variable combinations make function equal to 1. Because remember, the minterms, we focus on 1, don't we? The minterms of D are the don't care minterms and may be assigned either 0 or 1. The map simplification is shown in the figure. So we got 1, 3. Let me write this down instead of flipping back and forth. So we got 1, 3, 7, 11, 15. And the don't care is 0, 2, and 5. So I come down here in 1, 3, 7, 11, 15. They're all 1s. And then in 0, 2, and 5, M0, M2, and M5, where's M5? M5 is right there, automatically X's. Now notice here we included the X here and the X here with this first grouping, didn't we? Now going across the top, what can you say about all 4 of those terms? They all have different values, right? Like Y is 0, Y is 1, Z is 0, Z is 1. So that drops away. And you notice that the only thing they tell us is left is W prime X prime, which is our 0, 0. Because everything in this row has a value of W equals 0 and X equals 0. Does that make sense on that?
Yeah.
So we pair them together even though we don't really know they're 0s or 1s, do we? We really don't care. Now, I find this fascinating to me. It's just like, well, how can you pair them together if you don't know whether it's a 0 or 1 or it doesn't matter and have it cancel away like that? But it does. Because if I just took the middle 2 here, what would be left? Y or Z? Z. Yeah, because Z is both equal to 1 here, isn't it? So I would think, since logically it seems like, well, we don't know what those are and we don't care, there should be a Z here, but they're saying that you can treat these as 0s or 1s to cause things to cancel away. So that's interesting. And down here, for this entire column here, there's no X's, is there? And if you go straight up to the top, it's 1, 1, which is Y is equal 1, Z is equal 1. That's why they got the YZ. So that's how they get that value there. What in the world's that one? B. I assume that's the next example. Okay, and B. It says the don't care minterm 5 is included with the 1s. So this X that we ignored here, see how our grouping is such that we grouped it with these 4 together? And then this column here, we grouped these 4 together. Well, obviously this column here is YZ. You can pretty well see that. These right here, though, If I come over to the side, the W is equal to 0, W is equal to 0. That's where they get the W prime. And then if you come up here, what's the same for the columns of this square? The Z. Z is equal to 1, Z is equal to 1. That's where they get the Z at. And notice we get F is equal to YZ plus Y, or W prime Z. What do you notice about these two answers here?
They will start with YZ.
We'll start with YZ, and they're different, right?
Yeah.
So, again, that can be frustrating. It depends upon how you pair things up of what your answers will come up with. Let's see. Don't care midterms 5 is included with the ones. It says either one of the preceding two expressions satisfy the conditions stated for this example. So both of your answers. Previous example has shown that don't care midterms in the map are initially marked with X's and are considered as being either ones or zeros. The choice being 0 and 1 is made depending upon the way the completely simplified function is simplified. Completely specified function is simplified. Once a choice is made, the simplified function obtained will consist of a sum of minterms that includes those minterms, which were initially unspecified and have been chosen to be included with the ones. And they give you I guess we don't have time to get into that. Those are 4 variables. Well, we'll go ahead and stop there. So I'll go ahead and stop the recording.